does not happen. U belongs to C2 and V does not belong to C2 does not happen, which implies that any graph G which will satisfy this property has a property that it is 3 colorable, because what? So we can find a 3 partition, every vertex appears in one of the parts and each edge is going across. Okay, so that's it. Okay, what about Hamiltonian cycle? So I will not do it, but basically all we are saying that there exists H subset of my edges which is spanning, and for all V degree of V H is 2. Okay, so I will provide this slides, you can go through, and this is a slightly bigger formula, but what is interesting is that all these formulas length is is constant, like you can just count all these things, okay, which is constant, which implies that all these problems like 3 coloring Hamiltonian cycles are FPT parameterized by tree width. Okay, so there are 2 ways of using Kurzweil's theorem. The problem can be described by single formula, example 3 coloring or Hamiltonian cycle, or problem. So for those problem can be solved in f of w times n for graphs of tree width at most w, or so that implies the problem is FPT parameterized by tree width of the input graph. But sometime the problem can be described by a formula for each value of the parameter k. So for example, for each k having a cycle of length exactly k can be expressed as there exists v1 to vk in V, and these are adjacent to each other. That's it. So now notice that, like if I'm looking to find a k length exact cycle, then this problem is FPT parameterized by fk, the length of the formula, comma w. So then the problem is FPT parameter, like FPT running in time fkw times n for a graphs of tree width. So problem is FPT parameterized by combined parameter k and tree width w. So there are several ways of using this. So sometimes in a problem, the kind of problems we will generally people deal with, so they are able to at least get formulas of this kind, and secondly they are able to reduce the w to as a function of k, so everything will imply that it is a FPT parameterized by that function of k alone. Okay, so there are several ways we could use it, and whichever way we are using it, we have to say that this is FPT parameterized by this. So basically you should always remember that the Kurzweil theorem implies the problem is FPT parameterized by formula length, comma tree width. So if the formula length is constant, this becomes just w. If the formula length is also important, then you have to represent both formula length and w. So this is how, of course. Now think about your any favorite problem. Try to write a formula for that. If you are able to write formula in the language described by this, then you know that the problem with FPT parameterized by tree width. So this provided a uniform answer to all the questions which was FPT parameterized by tree width, and this was proved by Kurzweil's, and this is why it is called Kurzweil's theorem. Okay, so let's look at another example, subgraph isomorphism. So you are given a graph H and G, and we want to find a copy of H in G at subgraph, and parameter is size of the subgraph. So for each H, we can construct a formula phi A that expresses G as a subgraph isomorphic to H, similar to K cycle in the previous, right? So how we wrote, right? There exists V1 to Vk in V, and V1 and V2 are adjacent, V2. So for example, so suppose H is this graph, right? And this graph, then we'll say, okay, and suppose I want to, so there exists V1, V2, say V1, V2, V3, V4, so let's call it W1, W2, W3, W4, and W5. So we'll say, okay, there exists V1, V2, V3, V4, V5 in V, and this, okay, so we are thinking of W1 as being V1. So then what is, and what is this? There exists, and what happens? Adjacent V1, V2. Okay, now adjacent, you just, and you would put all the adjacency conditions, and this is the way you can express that H, there exists a subgraph isomorphic to H, right? By writing down these expressions, and for each of these guys, you like think of some names in their head, some symbol name, and you say, look, whatever the adjacency relation is, you just write here. Okay? Okay, that's it. So what does that imply? That implies that by Kurzweil's theorem, subgraph isomorphism can be solved in time f hw times n if G has tree width at most w. Okay? And since there is only a finite number of subgraphs on k vertices, subgraph isomorphism can be solved in time f k w n if h has k vertices and G has tree width at most w. So now you know that subgraph isomorphism is FPT parameterized by combined parameter k and the tree width. Now look, why we are saying combined parameter k and h? Because now the length of the formula here, whatever we are writing, actually depends on k, which is vertex set of h, right? And that is the reason why we wrote down this. Okay. Now we have seen several graph theoretic properties of tree width. We will see some more now. So it is known that some fact. So tree width is at most 2 if and only if graph is a subgraph of something called series parallel graph. Okay. And for every k greater than or equal to 2, tree width of k plus k grid is exactly k. So we have already talked about some of these things in our first week. So some more facts. And we also know that tree width does not increase if we delete edges, delete vertices, or contract edges. And hence we have shown that if f is a minor of G, then the tree width of f is at most the tree width of G. So remember what we said? We have also defined what is an f is a minor of G. If you can get, how can we get f from G? You start with G prime, which is a subgraph of G, which is basically means you have deleted some edges and vertices, and now you only apply some contraction operation to get f. So any graph that can be obtained from a particular graph G using this operation is called minor. And we have already proved that if a graph has a minor h, then the tree width of h is at most the tree width of G. And this is why this is also called minor closed properties. Okay. Okay. So what does this imply? The tree width of k click is k minus 1, and it follows from the fact that for every click k, there is a bag B, right, with k which is contained inside B, right? So if a graph contains a click of size k, then you know the tree width has to have at least k minus 1, because you will contain a bag containing all the vertices of a click, and this also we have seen in our first lecture. Okay, and so, but there is another. So what does this provide? So existence of big click implies tree width is big, but there is another structure which is not as dense as say click, but that existence also provides a existence of what is that called, big grid. So what is so this is the excluded grid theorem, which was proved by Seymour plus Robertson and Seymour in graph minor papers. Okay, what do they prove? If a tree width is large, then G has a k cross k grid as a minor. Okay, so a large grid minor is a witness that tree width is large. So if you do not have a small, if you do not have some big grid as a minor, then what you know, its tree width is small. So notice that this function, so this, let's spend some time on this function. So this basically was the function, if you look, 2 to the power k square log k. Okay, so they proved that if the tree width is like 2 to the power big of k square log k, then a graph contains k times k grid as a minor. Okay, but however they proved is that if I have a planar graph, then this is not true. So what is, if a planar graph has tree width at least 4k, then it contains k times k grid as a minor. Okay, so while if on a general graph existence of like you need an exponential lower bound on the tree width to prove an existence of k times k grid as a minor. On planar graph, like if the tree width is like tree width and grid are linearly related, means like if you have a tree width is just 4 power k, it has k times k grid as a minor. So it was a big open question in the literature on general graph. Can we say that if the tree width of G is more than some k to the power big of 1, then it has k times k grid as a minor? Surprisingly, it was open for long time before Chandra Chukuri and Julia Chuje showed it an upper bound of k to the power some 99 and some log. But after successive paper, now it has been shown that the tree width is even just k polylog in k, then that implies existence of k times k grid as a minor. Okay, so it is one of the very important and big theorem in graph theory is that this excluded grid theorem. So now notice if I can somehow prove that, oh, look at the graph does not have a k times k grid as a minor. What does it imply? The contrapositive of this implies the tree width of the planar graph is at most k, 4k. Similarly, on the general graph, if I say, hey, there is no k times k grid as a minor, which will immediately imply that the tree width is at most k to the power 10, for example. Okay? Okay. So, in fact, you can prove something more that every planar graph with a tree width at least 4k can be contracted. So not only you can contain k times k grid as a minor, but in fact you can get following kind of grid just by contraction. Okay? So look, so when we say that grid as a minor, what you say that, look, if a tree width is larger than 4k, then by deleting some edges and contracting, I can get k times k grid as a minor. But imagine that I do not allow you to delete vertices or delete edges, and only thing which you are allowed is contract. Even then we can show that we may not be able to get a grid, but we can get a grid-like structure, which you can see here, and it is also called partiality triangulated k times k grid. Okay? So not only 4k, tree with 4k implies k times k grid as a minor. In fact, it also implies something which we can obtain just from contraction. Okay, so now we saw there is another relation of tree width on planar graph that exists that is exploited quite a lot. So there is a notion of outer planar graph. So a planar graph is called outer planar if it has a planar embedding where every vertex is in the infinite phase. So just look at this in infinite phase, okay? And it is known that every planar graph has tree width at most 2. Of course, every outer planar graph is series parallel, okay? So in fact, what is interesting is that you can come up with a notion of what is called k outer planar, where you first, a graph is called k outer planar if it is a planar embedding having at most k layers. So what do you mean by at most k layers? So look at the vertices on the top layer, right? That is k. Okay? So look at all the vertices which are on the outer layer, give them a number k. Okay? Okay? That's one. Now if you delete them, okay, what is left is some other vertices, give them layer 2. So you can, what is the minimum number of layer that you can do this to achieve such that, okay, what you are left with, everything is outer planar, right? So the minimum number of layers you need to get to an outer planar graph is called k outer planar. Right? So if you need k layers, so for example, it is a, what we had was a 3 outer planar graph because we could reach this. Okay, so we had first, so you delete all the vertices which are on the outer planar layer or infinite layer. You get, after you delete them, you get another set of vertices which are on infinite or which are in the outer face. You delete them, you get another set of vertices which are on the outer face. If that is the only one, then number of times you have to do this is called outer planarity of the graph. And what is known is that is a very nice relation between outer planar and tree width, which we will exploit it for some of the examples or which we will see in a minute. So look at some of the applications we have. Okay. So now let's try to prove that subgraph isomorphism for planar graphs. So you are given a graph H and G, and parameter is K. So look at the layers of the planar graph as in the definition of K outer planar. Okay. And so you fix some integer S and 0 to K plus 1. Okay. Now let's delete every layer Li with I equal to S mod K plus 1. What is the meaning of this? So you have layer. So you give them layer number 1, 2, 3, K plus 1. Okay. Then again you call layer 1, 2, 3, K plus 1. Again you call 1, 2, 3, K plus 1. So I say now let's delete all the layers with number 1. Okay. Okay. 1, 1, 1. Right. Now after you have deleted it, right, what you have? Every component of a graph, every component of the graph is completely contained inside this, and every component has at most some K layer. Okay. So this is what means. You fix an integer 0 and you delete all layer with some mod K plus 1. Okay. Okay. What do you know about this? Right? So whatever you see that you are deleting different things. So you basically you delete some of these things and you will get all these pieces. Now what do you know? That every component is a K outer planar, and it is known that if a planar graph is K outer planar, then the tree width is at most 3K plus 1. Okay. So if a planar graph G has K outer planarity, then tree width of G is at most 3K plus 1. Now that's great for us. Why? Because why this is important? So suppose my H, look at this planar graph H, it has only K vertices. Now if it has at K vertices, then by pigeonhole principle, one of the layer 1, 2, K plus 1 does not contain its vertices. Am I right? So if it does not contain, say it doesn't contain, either it does not contain vertices from layer 1 or it doesn't contain vertices from layer 2 and so on. Like it doesn't contain vertices with, say, so what did we did? 1, 2, 3, K plus 1, 1, 2, 3, K plus 1, 1, 2, and this is why we call, so we made like, so what was this? L1 is like all 1 layers, like 1 from each, 1, 2, K plus 1, the first one, then next 1, 2, K plus first layer. So, and similarly, L2. Similarly, now what you know that because our graph only had K vertices, one of the layers, it does not contain any vertices. So if we have guessed the correct layer, then what you know, after I have deleted that guessed layer, then every connected component has at most K layers, and hence its tree width is at most 3K. So now we can apply our f of K 3K plus 1 algorithm of subgraph isomorphism and solve my problem, right? Now, if any of the if for any of the call of subgraph isomorphism we succeed in finding this subgraph, then we are very happy. Otherwise, what we know about this? We know that there is no subgraph, because if there was a subgraph of this H, then at least deleting one of these layers, okay, will preserve that subgraph, and we would have found this using this dynamic programming. So this is why it is called, in some sense, this is a very famous strategy which is used in polynomial time approximation scheme. We will see its application in a few minutes also. But you notice, right? This is like you divide. So it's like you divided your layers into 1, 2, 3, K plus 1, 1, 2, 3, K plus 1, right? So it's like 1, 2, 3, K plus 1, then 1, 2, 3. And then you say, look, imagine that it does not contain vertices from layer 1. So then it will contain only here, right? And I know, and the tree width of a graph is basically maximum of tree width of connected components. And each connected component has layers at most K. So the tree width of each connected component is at most 3K plus 1, which implies the tree width of the whole graph is at most 3K plus 1. And you will be able to find this pattern. Okay? I hope this is clear. Okay, so we do this for every s at most between this, and for at least one value of s, we do not delete any of the k vertices of solution, which will imply that we will find a copy of h in G if there is one. Okay? Okay. 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 Now let's detour to the approximation. Okay, so what is a C approximation algorithm for a maximization problem? Is polynomial time algorithm that finds a solution of cost at least op divided by C. And a C approximation for minimization problem is a polynomial time algorithm that will find you a solution of cost at most op times C. And there are several approximation algorithms for NP-hard problems. Like for vertex cover, they are factor 2 approximation, max 3 by set 3 set 8 by 7 approximation, metric TSP 3 by 2 approximation, and so on and so forth. Okay. For some problems, we have a lower bound, that is, there is no 2 minus epsilon approximation for vertex cover or 8 by 7 minus epsilon approximation for max 3 set, of course, under suitable complexity assumption. For some other problems, arbitrarily good approximation of them is possible. So, for any c greater than or equal to 1, say c 1.001, there is a polynomial time approximation, polynomial time C approximation algorithm. Okay? And there is a notion of what is called polynomial time approximation scheme. Okay, so what happens in polynomial time approximation scheme for a problem P? So it takes an instance of problem P and it takes a parameter epsilon. Okay, and it will always find you a 1 plus epsilon approximate solution, but the running time is polynomial in n for every fixed epsilon greater than or equal to 0. So what could be the running time? The running time could be 2 to the power 1 over epsilon times n, or maybe, some n to the power 1 over epsilon, or maybe n over epsilon to the power whole square, and n to the power 1 by epsilon square, right? So, so if you think of this, it's like we are trying to think of an P task as whether it is an FPT or XP algorithm in the parameter 1 over epsilon, right? So, you can do all kind of things here. Okay, some classical problems that have p-tasks like independent set for planar graphs, TSP in the Euclidean planes, Steiner tree in planar graph, knapsack, and so on and so forth. Okay, so let's look at this Bater shifting strategy for p-tasks. Okay, so there is a 2 to the power 1 over epsilon n times p-task for independent set for planar graphs. So you set d equal to 1 over epsilon. Okay, and now as we did it for this subgraph isomorphism, you look at your planar graph and you draw them outer planarity layer. Okay, and as always, what is this Li? Those I who leaves S when you divide by D. So all those layers who is like mod D. Okay, so now, so the result, so now if you delete any layer, what is the property of this graph? It is a D outer planar, and hence its tree width is at most 3D plus 1 order. So using the time 2 to the power w times n, there exists an independent set, for independent set, we can solve this problem in time 2 to the power big of 1 over epsilon times n. So what we did? So based on 1 over epsilon, we fixed a number d and we deleted some layers. Okay, and on each we solve the problem. And what are we going to output? So we do this for every s between 0 and 2, and we will output the layer with respect to which the weight of the independent set is maximized. What do you know about? So look at the pigeonhole principle. What does pigeonhole principle tells us? That look, this is some layer, this is some layer, this is some layer, this is, and these layers are disjoint. Right? Now, your independent set vertices are distributed among them, right? Now, when I say layers, this is like some set of layers L1, L2, and LS or LD, right? Now, look at the independent set vertices. By pigeonhole principle, at least one layer will contain at most 1 over D fraction of this, right? So, at most, so you would have returned, suppose the solution had size weight W. So what will you return? W minus, at least solution of size, you will return W minus epsilon yeah, so if you do this by pigeonhole principle, you will be able to show that you only lose d over you lose 1 over epsilon fraction, or not even 1 by 1 over epsilon fraction of the total weight, and you are able, and that if you do maths, you will get 1 plus epsilon approximation solution. So I mean, I leave this maths to you, okay? But the idea is that if the total weight was W for max weight independent set, there is you will lose how much? W, there is a layer which contains at most W by D. So you will definitely be returning a solution of weight this, and if you do maths, this will come 1 plus epsilon approximate solution. Okay? Okay. 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 So now let's go back to FPT algorithm. Okay. So this we have already discussed when we were talking about the applications. Why we care about tree width in parameterized algorithms. So I told you that look, using this DFS tree, either we can find a long path or long cycle, or we can compute a tree decomposition. Okay. Now if we can compute a tree decomposition, we can apply again Kurzweil's theorem, and right. Otherwise, the graph has tree width at most k minus 2. We have already done this, and then once the graph has bounded tree width, we did not do anything in our first week lecture, but now we know Kurzweil said that we can write down this formula, and using this we can show that finding a cycle of length at least k in a graph is FPT parameterized by k. Because why? Because the running time will be f of w comma times n, but w is here like where k is a length of the formula, which is k, and w is also become k. So you're done. Okay. So yeah, so we have already seen this, so we will I will leave this out. But this is the one thing which we have not talked about, and let's spend next 10-15 minutes on what is called bidimensionality. So up until now, we have been designing an algorithm with running times either c power k or k power k, but you have seen an algorithm via chromatic coding, okay, where we design an algorithm with running time 2 to the power little of k. What is the meaning of little of k? Is basically something like 2 to the power big O of root k log 1 over k, or maybe 2 to the power big O of k 2/3, but not like something little O of k. Okay. So for example, 2 to the power big O of k by log k is also 2 to the power little of k. And it's a very powerful framework to obtain efficient algorithm on planar graphs for this. Okay. So let chi_j be some graph invariant, that is an integer associated with each graph, and some typical example: maximum independent set size, minimum vertex cover size, length of longest path, minimum dominating set, minimum feedback vertex set. And our question is, given g and k, we want to decide whether x of g is less than equal to k or x of g is